So welcome to Gauss's Divergence Theorem Part 2. In this video we'll just be discussing two problems on Gauss's Divergence Theorem, and mainly we will be discussing the problem solving approach. So coming to the first problem, using divergence theorem evaluate double integral over a dot n ds where a equal to x cubed I plus y cubed j plus z cubed k and s is the surface of the sphere x squared plus y squared plus z squared equal to a squared. Now what does Gauss's divergence theorem say? The double integral over s a dot n ds will be triple integral over v divergence of a dv. And what will be divergence of a? 3x squared plus del by del y of the yj component, that is 3y squared plus 3z squared. So double integral over s a dot n ds will be triple integral over v 3 times x squared plus y squared plus z squared dv. Now we have the surface of the sphere x squared plus y squared plus z squared equal to a squared. So we convert to spherical coordinates as this is slightly easier. I have discussed spherical coordinates in an earlier lecture. So what we do is we put x as r sin theta cos phi, y as r sin theta sin phi, z as r cos theta. So the r limits will be 0 to a. What will be the theta limits? 0 to pi. Phi will be 0 to 2 pi. And dx dy dz, the Jacobian will be r squared sin theta. I have discussed Jacobian in one of my earlier videos, dr d theta d phi. So this becomes 3 times, because 3 is outside, integral r equal to 0 to a, theta equal to 0 to pi, phi equal to 0 to 2 pi. 3 x squared becomes r squared sin squared theta cos squared phi plus y squared is r squared sin squared theta sin squared phi plus r squared cos squared theta, r squared sin theta d phi d theta dr, because first we are integrating with respect to phi. Now if I take out r squared sin squared theta out, we get cos squared phi plus sin squared phi, which is 1, and r squared sin squared theta plus cos squared theta we get into r squared sin theta d phi d theta dr. Now what is sin squared theta plus cos squared theta? It is 1. So it becomes r squared into r raised to 4 sin theta d phi d theta dr. The limits be the same. So first we integrate with respect to phi. So we get r raised to 4 sin theta just phi, because there is nothing in phi within the limit 0 to 2 pi d theta dr. So that will be 6 pi, because when you substitute the limits you get 6 pi, r equal to 0 to a, theta equal to 0 to pi, r raised to 4 sin theta d theta dr. So that will be 6 pi, r equal to 0 to a. This becomes we're integrating with respect to theta now. So it becomes minus cos theta. Within the limits theta equal to 0 to pi, of course there's an r raised to 4 here. And this becomes minus cos pi, which is, take out the minus sign. So cos pi is minus 1, minus cos 0 is 1. So minus 1 r raised to 4 dr. And that will be minus into minus cancels, you get 12 pi, r equal to 0 to a, r raised to 4 dr. That is 12 pi, r raised to 5 by 5 within the limit 0 to a. So your answer is 12 pi a raised to 5 by 5. So quite a lengthy calculation at that. Now there's one more problem which I will be discussing. This is fairly easier. If f equal to 2xyi plus yz squared j plus xzk and s is the rectangular parallelepiped bounded by x equal to 0, y equal to 0, z equal to 0, x equal to 2, y equal to 1, z equal to 3, evaluate double integral over s f dot n ds. Again by divergence theorem, double integral over s f dot n ds will be triple integral over v divergence of f dv. And what will be divergence of f here? It will be del by del x of 2xy, which is 2y, plus del by del y of yz squared, which is z squared, plus del by del z of xz, which is x. So triple integral over s, triple integral over v becomes, the limits are quite simple here, x varying from 0 to 2, y varying from 0 to 1, z equal to 0 to 3, and what is your divergence? 2y plus z squared plus x dz dy dx. So integrating with respect to z first, keeping the x and y limits as it is, you get 2yz plus z cube by 3 plus xz within the limit z equal to 0 to 3 dy dx. So that will be integral x equal to 0 to 2, y equal to 0 to 1. Substituting within the limits, we get 6y plus 9 plus 3x dy dx. Now integrate with respect to y, so you get x equal to 0 to 2, 6y squared by 2 plus 9y plus 3xy within the limits y equal to 0 to 1 dx. So that will be 3 plus 9 plus 3x dx. That is integral x equal to 0 to 2, 12 plus 3x dx. Integrating, we get 12x plus 3x squared by 2 within the limit 0 to 2. Substituting the limits, you get 24 plus 6. That is 4 into 3, 12 by 2, which is 6. So your answer is 30. So we have discussed two problems on Gauss's divergence theorem. Thank you.